This video is part of a series for the Edexcel GCSE in Astronomy. This video is topic 8, Planetary Motion and Gravity. Now this video mainly focuses on Kepler's laws, how they came about, what they are, and how we use them. Now the story starts with Tycho Brahe, who was from what is now Denmark, famous for many things, including losing his nose in a duel over who was the best mathematician with his third cousin, and he had to have a synthetic nose for the rest of his life after losing part of the bridge of his nose. His body was exhumed in, I think it was 2010, when they tried to find out what his false nose was made out of. But the story doesn't start with Tycho's nose, it starts with the fact that he took very detailed observations of the celestial sphere. He kept very good records, and with naked eye observations he was able to plot the positions of the planets relative to background stars and make very precise measurements. Now Copernicus had placed the sun in the centre of the universe, but Tycho did not like this, and there are a few reasons for that. One of them was that Tycho believed in Aristotelianism. Aristotelianism is an idea that the physics proposed by Aristotle was correct. One of the things Aristotle proposed was that things move if forces act on them, and that if forces stop acting on them, they stop moving. Copernicus's model of the universe had the Earth moving around the sun, but Tycho couldn't see how a force could be applied onto the Earth to make it move around the sun. And so because he held on to this Aristotelian view of physics, he could not reconcile the observations that he made with Copernicus's model. Another reason that Tycho rejected Copernicus's model was religious. Tycho's interpretation of the Bible said that the Earth was an unmoving object, some unmoving body on which humans lived. And yet here was Copernicus saying the Earth went around the sun. But there was a third reason why Tycho rejected Copernicus's model. Copernicus's model put the sun in the centre of the universe, so as the Earth moved around the sun, there should be some parallax in the observations of nearby stars compared to further away stars. But no parallax could be observed with the naked eye. Tycho knew that the parallax that was predicted as the Earth moved around the sun could still be missed if the stars were much, much further away than Copernicus had suggested. But if the stars were that much further away, they would have to be much bigger in order to still be visible in the sky. And Tycho just could not believe the size that the stars would have to be to make those observations possible. An interesting fact that's going to be important later is the fact that Johann Kepler was Tycho's assistant. In 1572, Tycho observed a supernova. Probably a number of people observed it, but Tycho's credited as observing this supernova in the constellation of Cassiopeia. It was a very bright, very large star that he observed, and he couldn't reconcile the fact that there was no parallax across the year, which meant that this star had to be very, very far away. And he couldn't reconcile the idea that it was very far away and therefore was part of the celestial sphere with the current thinking, which was that the celestial sphere was unchanging. But Tycho coined the phrase nova for a new star, this supernova. So Tycho Brahe liked the Copernican system, where the sun was in the centre, because mathematically it was very close, it seemed to work very well. But he didn't like it because of a few observations that meant it wasn't quite right, but also this philosophical objection based on Aristotelian physics and his religious views about the place of the Earth in the universe. Yet Tycho recognized that the Ptolemaic system, where there were epicycles to explain retrograde motion, didn't work either, because there were times when Mars was closer to the Earth than the Sun was. And so this Tychonic system was proposed by Tycho Brahe. where the Earth was in the center of the universe, around the Earth orbited the Sun, and around the Sun orbited the other planets. Now, Tycho Brahe was not the first person to propose this type of system, but Tycho's system fits into the narrative just before Kepler's system. And Kepler's system was the most successful model of the solar system right up until general relativity took over. So what were the aspects of Copernicus' system that Kepler liked? Well, first of all, it was the idea of circular orbits, doing away with Ptolemy's epicycles. And secondly was the idea that the planets orbited the Sun. That did appear to be correct. And although the observations that Tycho did showed that Copernicus' system wasn't perfect, it was very, very good. It was very, very close. While Tycho was doing his observations to propose his model, his assistant, Johann Kepler, was working with him. And although Kepler did not agree with the ideas that Tycho was putting forward, he had to defend them. He had to write and debate and argue in favor of Tycho's ideas. Now, Kepler's history is fascinating. He had to flee his country because of religious persecution and this sort of thing. But we're not talking about that. We're just looking at what Kepler discovered. Kepler was fascinated with geometry, and he looked at how geometry fit into things like music, in the same way Pythagoras had done thousands of years before. But he also looked at other natural phenomena and how geometry played a part in those phenomena. One of the phenomena he was looking at, because he was employed by Tycho to make very detailed observations of the heavens, was the role geometry played in planetary orbits. And the physics was something Kepler wrestled with until he died. He couldn't explain the physics of why orbits were the way that he proposed they were. Part of the reason why he had so many difficulties with the physics was because he made some incorrect assumptions to start with. For example, his assumption that gravitational field strength, and therefore gravitational acceleration, was constant throughout the universe. There's no way you could reconcile that with what was observed. Remember, Kepler came before Isaac Newton and his law of universal gravitation. That didn't exist at the time. So the force that was responsible for causing the planets to orbit the Sun, Kepler didn't know what it was. And obviously religion offered an answer, but that wasn't good enough for Kepler. But he started by looking at the geometry and what I've written here, the harmonies of planetary orbits. And just by doing those observations and trying to link what he saw with geometry, he came up with 3 laws. And we call these Kepler's 3 laws of planetary motion. Now, this was a big moment. It was the biggest shift in understanding of the solar system since Copernicus put the Sun in the center. The idea that orbits were not circular but were in fact elliptical was a big change. Kepler didn't write his 3 laws in the way that we learn them now. Over time, they developed by other people, but they're credited to him because he first proposed the ideas that they're based on. But before we get into those 3 laws, we need to understand what an ellipse is. So here's a picture of an ellipse, and the most basic definition of an ellipse, without the helpful graphic, is this first statement here. The sum of the distance from any point on the ellipse to each of the foci is constant. I should say each of the foci. Foci is plural for focus. What we are saying is the distance from F1 to a point on the ellipse to F2, that distance is always constant, no matter what point on the ellipse you choose. A circle is a type of ellipse where the 2 foci, labelled here F1 and F2, are in the same position, 0 distance between them. Circle's technically an ellipse in the same way as a square is a rectangle, where the lengths of the sides are the same. So, here are Kepler's 3 laws. The idea that all planetary orbits are elliptical with the Sun at one of the foci. And actually this works for satellites orbiting planets as well. This isn't just planets orbiting the Sun. Anyway, the second law there, the idea that the rate that you're sweeping an area is constant. The diagram will make that more clear in a moment. And the third law there, and it's remarkable to think this, that Kepler came up with that law just by observation without any understanding of the physics, that the square of the planet's orbital period, that's how long it takes for the planet to go around the sun once, the square of that, so that's the time it takes to go round the sun once, squared, is proportional to the cube of the length of the semi-major axis of its orbit. Wow, that's a mouthful. So the semi-major axis is this distance from the center to the edge in the long direction. So in this particular case, the semi-major axis is length A on this diagram. Semi means half, and the major axis is this 2A length here. So if you take that semi-major axis, that's A on that diagram, and you raise it to the power of 3, that's proportional to the square of the time it takes for the planet to go around the sun once. All of this determined by looking at the observations and trying to match it to geometry. A real triumph. Now at this point, I'm just going to mention some technical terms that I may have mentioned in a previous video, but just in case I haven't, here they are. We look at the right-hand picture to start with the sun. The point where a planet is closest to the sun is the perihelion. Peri means close. Helios is the sun. And furthest away is the aphelion. Aph means furthest. Helion means sun. On the left-hand diagram here with the Earth, geo, the Earth. Perigee is closest to the Earth. Apogee is furthest from the Earth. So the diagram on the left is for satellites, such as Earth's natural satellite, the Moon, orbiting the Earth. The semi-major axis length is half the distance from the perigee to the apogee for the Earth, if we're looking at the Moon. And for the Sun, the semi-major axis length is half the distance from the perihelion to the aphelion. So Kepler's first law, all orbits are elliptical with the Sun at one of the foci. Well, this is here as a diagram. There's nothing at this other focus. There's nothing there. There's empty space. But the sun here and a planet orbiting in an ellipse. When the planet is here at the point we call perihelion, it is moving fastest. But when the planet is over here, aphelion, it is moving slowest. There's nothing at this point here. The sun is at the other focus. Kepler's second law is the idea that the rate of the area swept is constant. So what we mean by that, if you look at the diagram on the right, try not to be distracted by the other diagram, in a certain amount of time, the planet will move around the orbit a certain distance. The area that we sweep in that amount of time will be the same, regardless of where that planet is in the orbit. So when the planet is here, it sweeps around to here, in the same amount of time. It hasn't gone quite as far in terms of length because it's sweeping the same area and it's further away from the sun. And here as well. So all those areas labelled A are the same because all those times are the same. This diagram on the left is trying to show that. You'll see the slice is actually the same area, this blue slice, at all times. When the planet is travelling fastest, when it's at perihelion, that area, which is exactly the same, has to have a longer arc length because it is closer to the sun. Whereas over here, we're further away from the sun, so to have the same area, the arc length has to be shorter. Kepler's third law was that confusing law that we're going to get some practice in. The idea of the relationship between the orbital radius, actually the semi-major axis because orbits are elliptical, and the period of orbit, how long it takes to go around the sun once. If you were to plot the semi-major axis and the period on a graph, you would get a curve. But if you plot it on a log-log graph, like I've done here, well, I stole this off Wikipedia, but like you can see here, the gradient would be 2/3. Knowledge of how to draw log-log graphs and interpret them is part of A-level physics. It's not part of the GCSE in physics, nor is it part of the GCSE in astronomy. But what is part of the GCSE in astronomy is understanding the relationship between Kepler's third law and Newton's law of universal gravitation. Now I'm going to show you how to derive Kepler's third law from Newton's law of universal gravitation. This is not required for your GCSE in astronomy, but if you're studying A-level physics, this is a required derivation for that. Now, Isaac Newton derived his equation for universal gravitation from Kepler's third law. So we're working backwards here, but that's okay. Let's start with this equation here. This is the gravitational force acting on a body, F, is proportional to big M, that's the mass of, let's say, the sun in this case, multiplied by little m, that's the mass of a planet. Now, these two m's could be any two masses where there's a gravitational force between them. But because we're looking at planetary motion, we're going to say big M is the mass of a star, the sun, and little m is the mass of the planet. And the gravitational force is inversely proportional to the distance between those two masses, which we've labelled r. Capital G, the constant of universal gravitation, or the universal gravitational constant, is just a constant of proportionality. To turn our proportionality into an equation, Newton said that the gravitational force between two masses was proportional to the product of the two masses and inversely proportional to the square of the distance between them. So G just turns that proportionality into an equation. And Isaac Newton's genius was realizing that the same force that causes apples to fall on the Earth causes the moon to orbit the Earth and causes the Earth to orbit the sun. Remember, Tycho and Kepler didn't know what force was responsible for causing planetary motion. In fact, Tycho, if you remember, thought that it couldn't possibly be a force causing planetary motion of the Earth because the Earth's not feeling a force. And Aristotle said that forces are needed to make things move. Of course, this was incorrect physics from Aristotle. So that's the law of universal gravitation. The second equation here is the equation for centripetal force. Anytime a resultant force is causing circular motion, this equation applies. This equation says that the centripetal force, the resultant force causing circular motion, is proportional to the mass of the body undergoing the circular motion multiplied by the square of the angular frequency. Angular frequency is 2 times pi times the frequency. And the frequency is how many oscillations, rotations, orbits in one time period. So in the case of our planetary orbits, it's the number of times the planet will orbit the sun per time period, and we could use a year as that time period. And r is the radius of that circle in the circular motion. Now what we do for this derivation is equate those two. We say it's Newton's gravity that is causing the planets to orbit in circles. Now you can see a bit of sleight of hand there because the planets aren't circular, they're elliptical. That's Kepler's first law. But that's okay because circles are a type of ellipse, so we're going to go with it. We equate those two and we get this equation here. The rest is algebra. So the little m on both sides of the equal sign cancel. So you'll see that the orbital period and orbital radius has nothing to do with the mass of the planet at all. The masses of the planet, the little m, cancels out. But it does have something to do with big M. That's the mass of the star, the mass of the sun. Nothing to do with the mass of the planet, though. So then we're going to multiply through by r squared and divide through by omega squared, and we get this equation here. Omega was 2 pi f, where f was the orbital frequency. Remember, omega is the angular frequency. So we substitute that in to get this equation here. And now, because this bracket is squared, we square it to get 4 pi squared f squared on the bottom. Frequency is the reciprocal of time period. So I'm going to turn this f squared on the bottom to a t squared on the top. And I've written it like this because you can see everything here is a constant, gm divided by 4 pi squared. Well, 4 pi squared is obviously a constant. G is that constant of universal gravitation from back here. And big M was the mass of the sun, which is the same regardless of what planet is orbiting the sun. The sun is the same for all of them. The sun is the same mass. And we end up with this expression here. T squared, the square of the time period, that's how long a year is for that planet, is proportional to r cubed, where r is the distance between the centre of the sun and the centre of the planet. And then you can see for circular orbits this works. Kepler said it works for elliptical orbits as well. So how do we use Kepler's third law? Well, here's Kepler's third law again. And that means we can say this, that t squared is proportional to r cubed, just as we had before. Well, you can see that that means t squared over r cubed is equal to some constant. I don't know why I wrote that. But t is therefore equal to this. So if I divide this equation through by r cubed, and then take the square root of it, I get this. Everything here under that square root is a constant. So t is proportional to r to the power of 3/2. A half power is the same as a square root. So I've square rooted everything to get this equation here. Alternatively, I could have made r the subject. So if we go back to here, if I multiply through by r cubed, multiply through by gm, divide through by 4 pi squared, and then take the cube root of everything, I end up with this. The r is equal to this constant multiplied by the time period to the power of 2/3. So how can we use that? Well, let's remember that the time period is proportional to the radius to the 3/2. That's what we derived before. That means that time period was equal to some constant times the radius to 3/2. We're going to use that equation. But let's imagine I have some planet where the radius of its orbit is equal to twice the radius of the Earth's orbit. And I can write that like this. And I want to know what the time period of this planet is. How long does it take to go around the sun? Well, I could write the two equations like this. I could say the time period for this planet is equal to k multiplied by the radius of orbit of this planet to the power of 3/2. And I can say the same thing for the Earth. The time period of the Earth, which I know is 1 year, equals k r to the 3/2. And that's re, the radius of the Earth's orbit, 1 astronomical unit. And I could write these down as well. 1 astronomical unit, and the time period of the Earth is 1 year. Well, let's call this equation 1, and let's call this equation 2. What I can do is equation 1 divided by equation 2. Now, if I write that out, I end up with Tp divided by Te, and I know what Te is. I don't know what Tp is. And that's going to equal the constant divided by the constant. Well, that's going to cancel. And Rp to the 3/2 divided by Re to the 3/2. So we can cancel those constants. We can also say that the right-hand side becomes this, 3/2. That's how powers work. That means the time period for my planet P is equal to my time period of planet E multiplied by this ratio to the power of 3/2. And now I can plug my numbers in. So 1 year multiplied by this ratio, which was 2 Re divided by Re to the power of 3/2. Remember that my radius of planet P was twice the radius of planet E. So I've just replaced it with that. I can cancel my Re just like that. And now what I can say is that my planet P orbit time, my time period of planet P, is equal to the time period of the Earth, which is 1 year, multiplied by 2 to the power of 3/2. Or 1 year multiplied by 2 to the power of 3/2, and I can plug that into my calculator. 2.83. 2.83 years. You can't see that because I've gone off the edge of the screen, but there we go. 2.83 years. That's how long it would take a planet, which is twice as far away from the sun as the Earth is, to go around the sun. And you can do that with anything. If we say, oh, there's a planet with 4 times the orbital radius of the Earth, well, I could just do 4 to the power of 3/2, and that's 8. So a planet that is 4 times the distance from the Earth will take 8 times longer to go around. Is that right? It is. What about doing it the other way around? So we could do exactly the same thing we did last time. I'm not going to do the full working again. We're just going to use it this time. Let's say we have some planet, P, with a time period that's twice as long as the time period of the Earth. What's the radius of planet P in astronomical units? Remember that RE, in this case, is 1 astronomical unit, the distance between the Sun and the Earth. Well, I can just do the same thing. So 2 to the power of 2/3, that's going to be what my radius of planet P is. I'll take out my calculator, put 2 to the power of 2/3 in it. 1.59 astronomical units. And you can do that with anything. So I could do that with, I don't know, 4. A planet with 4 times the orbital period of the Earth. 4 to the power of 2/3 is 2.52 astronomical units, and so on. And so that's how you can use Kepler's third law. It does take some practice, but after a bit of practice, you'll be fine. Just remember this constant here does cancel out when you divide one equation by the other, and that's why you can just use the factor difference for r to get the factor difference from t, and vice versa. And there we have it. So this was the final video from paper 1, which is unaided observations. You can see we've covered everything in this list here, possibly even more so. And if you want to be notified when new videos are released, then all you have to do is subscribe to my YouTube channel, ring that little bell, and then you'll be notified. I'll be recording the videos for paper 2 very, very soon. Thank you.